Well, welcome back, everyone. Looks like we can begin. So for today's class, we have kind of a lighter class that we're getting through. We're looking at inverse functions once again. And the main reason for that is we have new functions we can consider taking inverses of, primarily the rational functions. And so this is kind of a review section, and also well worth it because inverses are kind of tricky on their own, especially with the new functions we have working on. Then with the rest of the time we have today, we'll take a look at the exponential functions. And this document, we're meaning to finish off probably on Thursday of this week. So we're not trying to do both of them at once today, just get a good start on that section below. Like I mentioned before, today usually has extremely low enrollment. So I'm glad someone in class suggested, how about an extra credit opportunity to show up in class, whether dressed up or not. I'll give extra credit if you're here today. And so that includes people on Zoom and people in person. I'll put in an extra credit opportunity on the Moodle to track it. It'll be titled probably something along the lines of Halloween extra credit, something like that. A 1 will denote that you got the extra credit. A 0 would mean that you did not. So if there's a 0 and you know you really should have gotten that extra credit, just email me and I'll correct it immediately. Aside from that, we have our quiz 10 that's due today. And I don't think I have any additional announcements. So any questions so far, folks, before we get started? Okay, well, let's begin then. We're in section 5.7, and this is going to be our last one for chapter 5. Then we're going to be turning to the exponential and logarithmic functions in chapter 6, and that's going to be our last topics for the whole semester. So we're very nearly done. Congratulations, folks. I feel like we've definitely been through a lot. And now, after saying that, here's this huge definition once again. Example 1 says, determine if the given functions are inverses of each other. And there's a couple ways to approach this. I think the last time we did this topic, someone in class just took one of the functions, calculated its inverse, and showed what's not equal to that. And so there aren't inverses of each other. And that's a great way to do this problem. Another way you could do it is through this formula above. We'll try it out this way. If you really have inverses of each other, then when you do this composition, you should only be getting x. And that x has to be in the domain of the function g. And you have to be able to reverse this to g of f of x. You must get x a second time. And that variable x must qualify for every x in the domain of f. But really, there's another definition here that's kind of hidden. Each time you do these things, say it's f of g of x, that's just the name of the composition, f of g. The way it's actually calculated is this, f at g at x. If we change the composition to g of f at x, then this is what you're really calculating here. G with f of x, the entire thing as its input. So that's kind of a strange definition. But the way we use it is, if it says determine if the given functions are inverses of each other, just take your f and g and immediately do one or the other composition. I'll start with the top. If it comes out as x, then we have to do the other composition and show that equals x as well. It's possible to write down a function where one comes out as x, but the other doesn't, which is really pretty weird. And that's the reason for checking both of them. On this one, let's color code this just to help the eyes to see what goes where. Here's the f and the g function. To start, I'm really just using that formula. F of g at x becomes f of g of x in this way. Next, we can make a substitution for that g of x function in green. We'll put in the entire 2x divided by x minus 1. On the next step, now we're going to the function f right here. So let's write this out in a template format. I'll color code this one in green, blue. So there was a parenthesis. There was an x variable here. We'll put a parenthesis instead of it. Same within the denominator, another larger parenthesis, and then minus 3. And the entirety of the input is 2x divided by x minus 1 in both of those parentheses. So 2x, x minus 1 will go here and here. Now our goal is to simplify this thing. It's just a mess as it stands out, or as it stands. But the goal for clearing this is to get rid of the denominator, x minus 1. We can multiply numerator and denominator by that. When it multiplies here, all you're getting left is just the 2x. Next, it has to multiply through to the into the denominator. When those multiply, you'll get just a 2x as well. Then it multiplies here to give a -3 times x minus 1. So now that the denominators are cleared, we want to expand it out. But we're trying to get to x if they are inverses. Already, it doesn't look too good. Let's keep on working on it just to see what happens. It's now equal to just a 2x in the numerator. In the denominator, it's 2x minus 3x plus 3. So we have a 2x minus x plus 3. And there's no other algebra we can do to this to try to simplify it. We can't divide this x into the 2x unless you also divide your 3 by x. It just makes it look worse if you try to do more work to it. So this is where I would write not equals to x. And then we need a conclusion. We can say this shows f, g are not inverses of each other. If they really were inverses of each other, we should have got the x that we were expecting from that top equation. But this whole thing cannot possibly simplify to x. And honestly, that's good for us because that means we do half the work. We just stop right here. Well, any questions, folks, with that review topic here? Okay, so this is just testing if we have inverses. On the next problems, we'll actually calculate them and see what they are. So example 2, this one's kind of a warm-up still. We did do an inverse of something like this, a square root function, back in chapter 3. But now we'll try it out again just to see how it goes. It's been a while. It says first, find the domain and range of this given function f. Domain's not too bad. We would just look inside the square root symbol. The radicand of x minus 4 has to be non-negative. So immediately write x minus 4 greater than or equal to 0. That's solved in one step. X has to be greater than or equal to 4. Automatically, we've got a domain here that's telling us all of the valid values for x that you could throw in. So let's write domain. I'm going to be more descriptive when I write the domain since there's really two functions we're dealing with, f and its inverse. So I'll say domain of f to specify which one we're talking about. So domain of f is, with a bracket, we start at 4, and then take all positive numbers larger than 4. So we're going from 4 to infinity. Now, one thing that's kind of weird about domains and ranges is typically the domain is the easy thing to calculate. The range is not. To get a range, you have to have a feel for what the function actually does. So let's just plot it really quickly right here. Actually, calculating the domain helps out the plot because we know the graph is only going to start at 4 and move to the right. So let's begin by putting down a point right at 4. 1, 2, 3, 4. And it makes sense it should start at 4 because a minus 4 here says the whole graph moves to the right by 4. So if we're thinking in terms of transformations, move right by 4. And the plus 3 will then say go up 3. So we'll go right 4, up 3. And that's just the first point on the graph of this f of x function. So if we want more information, you can throw in 5. If you put 5 here, it's a square root of 5 minus 4. It's a square root of 1, becoming 1. Then plus 3, we get a value of 4. So here's our next point. And we're not looking for a picture-perfect graph. I wouldn't try to do too many points, just enough to get a feel for it. Square root function transformed in that way then looks like this. It's like half of a sideways parabola, where that's the missing portion right there. So once we have this, now the range is not so bad. The range is the extent of all the second coordinates. It starts at 3, and it just goes upward forever. So range of f is going to be from 3, then going off to positive infinity in that way. Well, we've got domain and range. Now we can find the inverse, and we'll find the domain of range of the inverse as well in the next steps. But first, any questions, folks, on this warm-up question right here? Okay, pretty much everything right here is right out of chapter 3. And so is the inverse portion right here. To calculate the inverse, I would usually start by writing f of x equals y, or y equals f of x, up to you. I mean, this is the function right here, y equals f of x. So if I write f of x equals y, the next thing I would want to do is make a substitution for f of x. Its formula is root x minus 4 plus 3 equals y. So this would pretty much be my step 1 in this process. Anyone recall what step 2 would look like? We have to do something with the x's and the y's, but it's definitely a weird something. Anyone recall just what it was? Not quite setting x to 0. Exactly. Everywhere you see an x, make it a y, and everywhere you see a y, make it an x. So we can indicate it kind of like this. Swap your x's and your y variables. So if we make that swap happen, it's going to turn into root y minus 4 of step 2 plus 3 equals x. And now we're definitely well on our way on step 3. The next thing we're going to do is solve for y. And this is really the last major step on this. I usually do a step 4 where we're going to write our answer as f inverse of x, but I wouldn't take off points if you didn't do that last finishing touch. So let's solve for y. First thing you want to do is, well, I would say square both sides, but with that plus 3, it's a really, really bad idea. Let me put this on temporarily, and I'm going to delete it in a moment. If you did this, it seems okay at first because you're trying to eliminate the root. But the thing on the left, you truly have to FOIL it out now, and the problem becomes worse. So you're going to get square roots spread out all over the place in that case. It's best to, if you're trying to solve for y, isolate the entire square root. Then when we square that, we won't have to FOIL something involving a square root. It'll be much easier to isolate the y variable. So let's start by just subtracting 3 from both sides. It's now the root of y minus 4 is x minus 3. At this stage, we can square both sides. That's kind of a special step. So let's use purple here. This is raised to power 2. Then this is raised to power 2. And it turns out the squaring function and the square root function, they are inverse to each other. And when you do that kind of operation, you've canceled both the power and the square root. You just get the input of y minus 4. So now y minus 4 equals x minus 3 squared. And in the answer, I'd probably just leave it in this format. It's going to be in vertex form, and that's a really good format for a quadratic anyways. Yeah, go ahead. True, yes. So sorry, I had to think about that question for a moment. If you went something like this, the root of x squared, you would get the absolute value of x, absolutely. And that causes all sorts of havocs in equations and solving. But if you go like this, let's see here, the root of x to power 2 in this way, in this case, we would just get x itself. And that's the kind of the way we're operating on this side. Let's see here. Well, the thing inside that y minus 4, it turns out it couldn't potentially be negative because your y coordinate is at, let's see here, it was really an x coordinate. It's at 4 or higher is the only thing that it could be inside here. So the thing inside the root is actually a positive quantity. I was thinking the y was 3 or higher, but that's confusing because we swapped x's and y's, right? The x itself started at 4 and it's only larger. So we had no possibilities of negative there, and they just wiped each other out in that way. Does that make sense with that operation so far? Awesome. Then last thing to do, add 4 to both sides. Y equals x minus 3 squared plus 4. And here's the last finishing touch. Oh, let me make a quick record here. Okay, just make sure you've got that extra credit. Anyone else came in just a bit ago? Okay. So once we have this, the last step, here's our step 4. I would just finish this off by saying After getting a little bit more space, it almost fit. F inverse of x is x minus 3 squared plus 4. So now we have the inverse function. It's right down here. And just for fun, let's put it up on this graph just to see if it even looks right. Any questions or comments at all, folks, so far? Okay, let me scroll out for just a bit so we can see everything all at once. Now, this function right here, it is a polynomial function. So we typically think of it as having a domain, all real numbers, but that's not the case this time. The context of this inverse function is that we were inverting a square root function that did have a limited domain. And so now when we go to plot this, we have to switch things around. The domain of f inverse is the range of f. We'll write that down in a moment. And the range of f inverse is the domain of f. But the main takeaway is that's the domain of this quadratic function right here. When we go to try to plot it, it's going to move to the right by 3 and then go up 4. So right 1, 2, 3, up 4, places a dot here. And then the rest of the parabola would be plotted in about that way. So this is y equals f inverse of x. And really the only reason to complete the sketch by adding a second function on there is it's kind of a check. If everything has been done just right, then there should be a reflection across this line, y equals x. So every pair of invertible functions, when you plot them, have this feature right here. And this was hand drawn, so it's not even supposed to look perfect, but it doesn't look too bad. If you printed it out, fold along the red line, y equals f of x curve and y equals f inverse of x as a curve should overlap. So now last thing to do is just state the domain and range. We could state it from the graph if we wanted to. That's working a little bit hard. Or use this as a formula from chapter 3. I would write domain f inverse to start, since that's what we're trying to find. And it's in purple because this is really a formula in its own right. The domain of f inverse is automatically the range of the original function f. So we go look up what that was. This is the major reason why we calculate domain and range to start. It goes from 3 all the way to infinity, like we saw in the graph. The next formula, also in purple, is that the range of the inverse function, so that's the range of this function here, we go all the way to the top, and it's the domain of the original function. So domain of f, which is then equal to 4 to infinity. So finally, that's the full process. If we scroll out just a bit, yeah, that's about what it would look like. If I never even calculate f inverse down below here, we could have just taken these points, interchange x and y's, and get these related points on the graph here, like we plotted a point here. And we could have said just immediately, well, the domain looks like it goes from 3 to infinity, and the range looks like it goes from 4 to positive infinity as well, just from the graph alone. Well, again, that was our chapter 3 review problem on dealing with these kinds of things. Any questions at all, folks, on getting through this one? Okay, this is a pretty short section. It's pretty short in Alex as well. I have just 2 more problems to take a look at. And also, the name of this section is kind of weird. It says inverses and radical functions. A radical function would be something like that one. That's a square root function, so it's a radical in nature. And this one is a cubing function that's been transformed. When we go to invert this, we'll get another radical function. That's the only reason that's part of the title. That's the kinds of things we're inverting on these notes. And example 3 is just a really fast one. It just says, calculate G inverse. That's all we want here. No worries about domains, ranges, or graphs, or any of that. So let's give this one a try. We can start off by really the same kind of thing as before. Write G of x equals y. All this is pretty much my step 1 here. Next, substitute inside G of x, the given function, which is x minus 3, cubed plus 18, is set equal to y. So that's our step one. For step two, we'll do this operation again. Swap out our x's and y's. And that gets us to the point where we're ready to start actually solving the equation. So this is now y minus 3 to the power 3 plus 18 equals x. So step 3, just solve for y. But now solving for y, in a really strong sense, it's pretty similar to what we did right over here. We had a squaring function that had to be eliminated, so we used a power 2 function to make that happen. This time we have a cubing function, and you want to see what kind of function we could use to eliminate that power 3 right there. You could expand it, but because you're solving for y, you would probably want to factor it back because now y would be in multiple locations after the expansion. But if we wanted to, we could eliminate that power 3, except that it's a dangerous step to do right now. That's kind of weird. So I'm going to write something I want to delete in just a moment. But the strategy would be is, if you want to destroy that power 3 and get it out of there, you want to do this step. Take the cube root of both sides. But just like in the last problem, I don't want to do that right now because if I take the cube root here, there's actually no cancellation. The positive 18 has to be taken out first, and then we can make the cancellation go through. So first step, isolate the power 3 function. Let's subtract 18 from both sides, and it's y minus 3 cubed. Now x minus 18. At this stage, this is the major operation we want to take. The cube root of y minus 3 cubed becomes equal to the cube root of x minus 18. And here's a really short explanation of why we have to take the cube root specifically. If you have something that looks like this, a to the power 3, so just as a general formula, and let me take those off. Let's suppose you cube root that a power 3. Then you could rewrite this whole thing as a cubed, and your cube root here is truly an exponent. It's a power of 1/3. So power 1/3 would go right here. But now exponent laws take over. If you have an inner power of 3, and the whole thing is raised to an outer power of 1/3, exponents would multiply. This would become a cubed times 1/3, resulting in a power 1 or just a. For us in this problem, it is visualized this way. Think of y minus 3 as the a. The cube root power 3 cancel off. And this one's even more friendly than the last problem. It doesn't matter if the thing inside the radicand is positive, negative, or anything at all. A cube root is not worried about those kinds of things. And the right-hand side, I'll just continue to write it as cube root x minus 18. So we're still solving for y. Next step, add 3 to both sides. We now have a cube root of x minus 18 plus 3. And here's the fourth and final step, really just paraphrasing what we found. If that was the original function g of x, then we found g inverse of x. It's by the formula cube root x minus 18 plus 3. And that's pretty much how the whole problem goes. If you start with the power 3 function and you're inverting it, you're getting a cube root function is a takeaway on this problem. And if you swap that around, the last problem started with a squaring function. Or excuse me, square root function. We inverted it and we ended up with a squaring function instead. So in a certain sense, inverting something is all about messing with that kind of power for dealing with some kind of polynomial equation. But that's the end format here. If you did this one on Alex, these problems can be a little bit long because there is a lot of steps here you have to go through. And so you could save a ton of time by doing a fast check, just like we did before with the graph. Let's do it ourselves with Desmos to make this happen. So first thing we put in is just the original function. It's equal to x minus 3 cubed plus 18. They told us it's an invertible function. And at this stage, I'd probably trust them. It looks like it passes the horizontal line test, allowing for invertibility. Now let's put in the inverse, we found a cube root. Now we actually have to use this trick right here of the power, because I'm not sure how to put a cube root inside out of, not Alex, what is this, Desmos. So I'll type this in as G about G of X. I'm not sure how to put an inverse symbol at all in these kinds of things. So we'll think of that as its inverse. It's X minus 18 to the power of 1/3 plus 3. It's kind of hard at this stage to tell if they're inverses to each other because our visual check should look like this. We need the line y equals x added to the graph so we can tell whether or not it's really inverted. So let's take another look. Let's add y equals x to the graph. And that looks pretty good at this stage. If we expand this out, zoom out a little bit, then that's pretty much our function. The original one is in red. We reflect across y equals x, and the inverse function is right here in blue. Let's take a screenshot of that. And that's pretty much the check. It's a really fast check, so it's definitely worthy of doing. That turned out really, really big. And that means this whole question is pretty much done at this stage. Any questions or comments at all, folks, on getting through this one? Okay, well, we did it. And because it's Halloween, this was the one where I thought I could probably make it look a little bit spooky in a way. So here's our graph right here. And if we take this graph and kind of move it around, now it looks like some kind of demon of some kind. Let's see if we can make this look like a Halloween thing. You could say there's eyes here. Let's make it really pissed off looking. There we go. And maybe fangs or something like that. And we've got a proper vampire. So happy Halloween, folks. That was as bad as silly as I get in class normally. That's not too major. Sorry, I was trying to make a Halloween themed problem, and that's as close as I got on this one. But we definitely have an inverted function, so we hit the math topic as well. Any questions at all, folks, on getting through those? Okay, well, let's try out another one. This is the last one for this section here. And finally, we're dealing with a rational function, but same kind of thing as before. In fact, we even inverted these kinds of functions way back in chapter 3, even before we called them rational functions. So same kind of process, but this one wants domain to start. Then we'll calculate the inverse and then state the domain and the range of the inverse. So it's asking for the same kind of information, but in a weird way. I'm not going to try to get the range up here because that is really, really hard. You would have to graph the function, and that's already a major process, just graphing the rational function itself. That was our quiz, it takes many steps. So to get the domain and range of this inverse function, we'll walk to it in pieces. First, we'll find the domain of this one. When we do that, the thing that we're worrying about the most is that denominator right there. If it ever hits 0, we have a non-domain element. So we take 9x minus 10, set it to 0, and I should turn off ink to shape. We got a circle somehow. Oh, geez. Microsoft Word is really pissed off. Okay, I think it's back to normal. So we've got 9x minus 10. Set that to 0 and solve it, and we get 9x is positive 10, or x is 10/9. So that's the one value that f cannot take. If you put 10/9 here, you divide by 0. That means everything else is fine, and we can write that domain of f is everything but 10/9. It's kind of nicer to say in words, but writing it out in interval notation would look like this. All numbers less than 10/9, union, or you could say together with when you write that symbol, all numbers larger than 10/9. And we definitely have to use parentheses on both because the minute you use a bracket, you're saying 10/9 is in the domain, but that would allow the division by 0. So now that we've got the domain of that, we're going to calculate the inverse and then somehow get both domain and range of the inverse. Again, it doesn't feel like we're able to do that, but it really works out for this. Because if you have the domain, you've already got the range. We'll just swap that around like we did before. And to get the domain of the inverse, we just need to know what it looks like. If it comes out to one of these, we'll find its domain pretty quickly. So let's start off the process. I'll write f of x equals y. Then we make a substitution for f of x. It's all of that stuff. 7x minus 8 divide by 9x minus 10 is now set to y. And we're just doing this in a really, really methodical way, since finding a function inverse, it's like a recipe with 4 or 5 different steps, depending on how you write them out. But if you ever did it this way, if you went from here just directly to this, because you've been inverting them for a while, you know what the process is, you know what that next step should be, that's okay as well. This is really just a guide to get right here. So you could break it up or just do it in one shot. But however you do it, we still have to solve for the variable y. And if there's a denominator in the formula, best to just clear that denominator. So let's multiply both sides by 9y minus 10. On the left-hand side, there's an immediate cancellation, and it's just 7y minus 8. On the right-hand side, we have multiple problems, but we can start by just distributing x through that group to get 9xy. That's a 9 minus 10x. And we need to get y in one spot. We can do that by subtracting 9xy. Let's write that out carefully, since now a lot of things are going on. We're going to subtract 9xy from both sides. We want to collect all variables involving y to one side. And everything that doesn't involve y will move off to the opposite side. So it's also add 8 to both sides as we go. Now, these are not like terms, so when we write them out by the red dot, it's just going to be 7y minus 9xy. Here, they are like terms and they cancel, so we can go directly to the equality. These cancel as well, and right up here, we could make it 8 minus 10x, or negative 10x plus 8 if you prefer. So far, here's what the process was. We eliminated y from the denominator. Now it's on both sides of the equation. We did some addition, subtractions. Now y is only on one side of the equation, but it still has to be in one spot. So we use our factoring trick, factor out to y from the right-hand side, and you'll get 7 minus 9x equals 8 minus 10x. And you have y finally solved the moment we divide by 7 minus 9x here. So y equals 8 minus 10x, division by 7 minus 9x. And you're pretty much done right here. The last thing you could do, just to be specific of what you found, again, it's a good strategy because f inverse is referred to. It makes the next steps a little bit easier to read. I would definitely write f inverse of x equals 8 minus 10x, divide by 7 minus 9x. Just as a reminder, that's the inverse function we have just found. Then if we'd like, we could check it out on the graph. I think we're pretty good on this one. Yeah, go ahead. Sorry, say again. You're saying 0 for the denominator? Yeah, that's going to be how we get the domain right here. The 0 would change on this one for the denominator. So we have a different kind of domain versus what we got on this one. But we're going to attack it pretty much the same way. Set the denominator equal to 0, find that domain. And let me actually take a quick screenshot right here. Let's carry that down. So the last steps is truly pretty tricky. And there are problems like this in ALEKS where we have to worry about domains and ranges. Let me get that all settled. There we go. But all we really have to do is, like you were mentioning, to start with domain, just look to that denominator, set it equal to 0 and solve. Really just how we started off the problem. So 7 minus 9x set to 0 will give us a negative 9x set to negative 7. And so x would be equal to 7/9. Microsoft Word is having a bit of a fit there, but we'll just ignore it and hope it works out. So that's the entry that cannot be in the domain of f inverse. So let's write domain f inverse, just to be specific, so we know which domain we're talking about. Goes from negative infinity to 7/9, and then from 7/9 off to positive infinity. So that's what gets us our domain there. Last, to get the range, we just use this formula again. Let me write it in purple since it's definitely a formula. Range of F inverse, we can write a little bit more compactly as range of F inverse. Think of the of as parentheses now. It's automatically domain of F by formula. And so we can come down here, just look it up, what we said in part A, and write it in as negative infinity to 10/9 union 10/9 to positive infinity. So that gets us both domain and range in one shot for that inverse function. Well, any questions, folks, on finishing off this one? Okay, it's kind of a weird choice on the book to have a inverse section in chapter 3, and then again in chapter, I think we're up to 5. But it was a good choice because I think function inverses are tough, and they're also some of the most useful things that you could take away from college algebra. In the next section, we're going to take a look at, we're going to be trying to solve these equations. So you can think of chapter 6 as having this as its major goal. Solve 2 to the power of x equals maybe something like 10. We'll be looking at more and more involved equations, but notice immediately the difficulty with this equation. If it was 2x equals 10, no problem, right? Just divide by 2, x is 5. But this one has a massive, massive problem. You can't divide by 2 to fix this. Yeah, go ahead. Exactly, we need a logarithm to fix this. And how do we get a logarithm? A logarithm is the inverse of an exponential function. So I think that's pretty much the major reason these notes are here. We're about to get into weird looking functions. This one's an exponential. And to solve them, we need an inverse function, the logarithm, like you mentioned. Well, let's put that here just as kind of a takeaway of why are we doing inverses when we already saw them in chapter 3. Again, it's probably a really good call. To solve this, we need an inverse function. And as a preview, just like you mentioned, Michael, the inverse function on this one would be a logarithm. We need a logarithm to base 2. Or really any logarithm would work, but logarithm base 2 is specifically the inverse of that function right there. So that's pretty much what the rest of the notes are going to be about in chapter 6. Dealing with that as a function and the logarithmic functions that are going to help us to solve this equation here. Well, any questions at all, folks, before we take a look at these? Okay, let's save this up. And congratulations again, we're done with chapter, I forget which one this is, chapter 5. This one was a slog, the polynomial functions, fundamental theorem of algebra, the zeros of polynomials. I think that's the more difficult part of this course. But in chapter 6, it's really not too bad. So let's open that up and see how it goes to start. Those were just the announcements. So 6.1, it's kind of a slow introductory kind of a section. We're going to introduce the new class of functions called exponential functions. In 6.2, we'll see how to graph them. And then we'll notice that every time we do graph these things really carefully, they always pass a horizontal line test, which means these functions turn out to be invertible. And that's what's going to walk us into the later sections on dealing with the logarithms. So for any real number x, if your function has this format, you're looking at an exponential function. And there's a couple ways to write this out. For example, down here on the example, the a would have been 2, or excuse me, the a would be 3, the value that's in front. B for the base would have been 2, but I can't necessarily write it this way. Because now it looks like we're taking 32 to the power of x. So the functions are kind of annoying with the way you write them out. Here it's clear only b is raised to the power of x. But here I have to be more specific. You could go 3 times 2 to the power of x like this, if you're indicating that your base is 2 and not 32. Or this does the job decently as well. A parenthesis is now indicating it's only 2 that's being raised to the power. So that base right here is the base to the actual exponent of x, and the base has to be positive, and it can never equal 1. There's good reasons for that. Let's check it out on Desmos. Let's put in a really fast function. So let's make it be y equals 5 to the power of x. So my a is 1 now. My base b is a 5. And that's about what the graph would look like. So if I put in a 2 to the power of x, it's still exponential, 3 to the power of x. Notice they all cross right here, no matter which one I put in. But if you ever allowed your base to equal 1, here's what would happen. It's just boring. It's a horizontal line. This is literally the equation y equals 1. You're just raising 1 to the power of x. It's going to be 1 itself, whether the x is there or not. So that's the only reason we're eliminating that possibility for b. But it can be, say, numbers different than 5. So if you have something that's larger than 1 as your base, it's blowing up, getting larger and larger as you cross this one. But put in a smaller number, like say, not z, 1/5, it's like the whole graph has been flipped around. There's an actual real transformation going on there. This y equals 1/5 x has caused a reflection across the y-axis. And the best way to see that is, it's all about the exponent laws there. But still, we're putting in positive numbers. So one question folks have is, why can't the base be negative? Well, here's what happens on the graph. Let's see how Desmos handles this. I'm not going to handle it at all. It's very upset with that. Nothing plots. And here's the trouble with that. If you try to put in a negative base, say -3 power x, where x can be any number now. Let's say x equals 1/2. You'll have -3 to the power of 1/2. But that's just the square root of -3. This is complex valued now. All of a sudden, out of nowhere, it didn't look like that would happen. This becomes I root 3. And that's the whole reason why we want positive numbers. We're trying to get real valued results. The moment your space becomes negative, well, some of them are real numbers, but there's a whole lot of them that are complex valued. Desmos doesn't even want to mess around with that function. It just gives up. Nothing is plotted here. Kind of strange. So those are the only requirements for our base. We need a positive number, not equal to 1. And as far as the a, we just want to make sure it's not 0. If it was 0, the function is just 0. But it's often called an initial value. The reason it's called that is, if we take this function here and put in, say, a 0, we would get a times b to the power of 0. But b to the power of 0 is a 1 here. This would just turn into a. A lot of these functions have a time component when we're doing them in applications. So we would think of this at time 0. The value is a. So let's say the initial value at 0 is a. That's the only reason we like to call it the initial value when we're dealing with the function. So that's pretty much it. Our exponential functions come with an initial value, a base, and now x can be any real number whatsoever. That means the domains of these is all real numbers. And we saw the ranges when we put in something normal. Looks like all positive real numbers. But we'll do a lot more information on that in section 3.2 when we're trying to look at the properties of the graphs a little bit more carefully. For us to start out, probably the best thing we could do is, let's just complete our own table like this and plot our own exponential function. There's one like this as well in ALEKS. And honestly, it's a pretty interesting review of exponential notation and exponent properties. So let's work this out carefully. Our function is 3 times 2 to the power of x. We're trying to plot this thing, so we need a table of values. First, we're plugging in a -2. At a -2, we're throwing it inside here. We'll get that y equals 3 times 2 to the power of -2. I thought that would fit when I double spaced that. I think I need a little bit more space for all these. Now, when you have a negative exponent like this, here's what happens to it. This turns into 3 divided by 2 to the power of +2. So the exponent property here is, if I want to make that a positive exponent, and we definitely do, it's easier to work with, we just change its position from the numerator to denominator, or vice versa, and also change the sign of the exponent. Now it's a +2 power. So this becomes 3 over 2 squared, which is 4. So 3/4 is our first point. Then we just rinse and repeat. But does that make sense to folks on that first evaluation? Okay, let's keep on trying this. Next, we're putting in a power of -1. It's going right there for x. So this will be y equals 3 times 2 to power -1. Just like before, we need to do some surgery with those exponents, force them positive to get a value out. So 3 stays exactly where it is. 2 goes to the denominator, but now with the power +1. But 2 power 1 is just 2, so this becomes 3/2. And then pretty much rinse and repeat. Next, we're plugging in 0. We have 3 times 2 power 0. We've done that once before. A base raised to power 0 is automatically a 1. So this just turns into a 3. And now that we're looking at this table, it's kind of an interesting table. There's a pattern on how all these values are truly emerging. We went from 3/4 to 3/2 to 3. That means we're multiplying by 2. And if that pattern were to continue, I bet you we could predict the next results. I'll put it here temporarily. We'll work it out carefully just to see if it works out. So those are the predicted values that we ought to get if this pattern does continue. And let's take a look. Plug in a 1 next. That's 3 times 2 to the power 1. 2 to the power 1 is just 2, so this is a glorified 3 times 2 for a value 6. It looks like it is working. Now put in the power of 2. Well, that means the power here is just 1 higher. That's 2 squared. That literally means you're just multiplying by 2, right? You're multiplying by an extra base of 2. Writing it out, here's what it looks like. 3 times 2 to the power 2. That's 3 times 4 for a result of 12. At this stage, I'm convinced we'll get 24, so let's just go through the motions. 3 goes here. It's 3 times 2 cubed. 2 cubed is 8, so this is 3 by 8 for a value of 24. And this is not a coincidence. Exponential functions always have this feature right here, that you get to the next values. If these are only changing by 1, increasing by 1, you're just multiplying by something. It could be multiplying by 5. It could be multiplying by a third, anything like that. But now that we have all these values, here's the punchline. We just want to plot this stuff. All of the results are positive, so we can focus on really just quadrants 1 and 2. We plot at -2. Oh, let me try again. That's -1, -1, -2. And then we went 1, 2, 3. So starting off, our first value, well, let's see, we have 3/4 all the way to 24. Let's just see how high we can go here. 1, 2, 3, 4, 5, 6. We're going to go off the charts, but that's okay. It's exponential. It's going to happen for these kinds of things. 7, 8, 9, 10. Didn't quite get to 12, but at least we have 10 on here. Now for the graph, we have our first value of 3/4. That's a 0.75 at -2. To my eye, it looks about like that at 0.75. At -1, it's 1.5, so about here. Then at 0, we have a height 3. At value 1, we are shooting up to 6. So it's growing extremely rapidly, but we're doubling the values every time. I mean, if with this kept on going, we'd be at very, very large numbers. At 2, we're at 12. I'll put a dot 10, 11, 12 about here. I think that's the last point I can realistically put on this graph. It goes like this. Once we get across the y-axis, the growth rate is so severe that I don't think I'm really capturing it too well. That curve sort of missed a little bit, but that's all right. If we go this way, to the left of the y-axis, it's now decaying towards zero. It'll never actually connect. So we have a true horizontal asymptote of equation y equals zero on this graph, which is kind of a surprise, I'd say. Then it'll always have some kind of intercept on the y-axis. Here it's right at 3. That's not a coincidence that that's where the initial value came into play. So 3 in this problem is the initial value. And yet if you plug in 0, the graph starts at 3 at that location. Then it just shoots on up. Well, we did it, folks. That's really, I'd say the big takeaway with this is some of the exponent laws and then looking at the graph. But another surprise about these kinds of things are they're always a horizontal asymptote. Also, if you look at that graph, that's invertible. It'll pass the horizontal line test. So we can put a line that goes like this and try to find this function. This one right here is going to be the inverse of f of x. Really just there for extra information, since that's our real whole goal in this chapter 6, to get the inverse of that function so we can solve more interesting equations like we indicated before. But we did it. That's a problem you'll see in ALEKS, so it's kind of a tedious one. I felt like we have to do one ourselves, but it lets us to see the graph and get a stronger feel for exactly what we mean when we say exponential function. Functions that look like these things. But let's try out another problem then. For the notes, there's several problems that are really just fast exponential functions with different scenarios. They're definitely word problems, but they're kind of fun and they're really fast in this section. There's no crazy problem solving like we've seen before. And I think where I want to end on the notes today is right before this. The compound interest formula is the first big formula in chapter 6. I want to give that a try once we return on Thursday's class, since that's kind of a nasty formula to start right at the end of class. So we'll try it for a couple applications. This is a nasty one from ALEKS itself that we'll give a try if we have time. Let's start off here with the 2023 convertible Corvette Stingray. So we have an exponential function. It's going to model the value of this Corvette 2 years after purchase in 2023. I don't know how accurate this model is, but it might be pretty accurate for our market. It says this convertible Corvette Stingray is predicted to have a dollar value given by this equation. V for value, it's going to start off at $195,379. The 0.73 is raised to a power 3, but that means every time a year increases by 1, we're losing 27% of the value. So 27% of its value, that I don't think is an actual contraction, but I'm not completely sure. I'll just take it up for now. 20% of its value is removed each year. Again, it is a made-up problem, so this is not necessarily our card market. But now we need to know, what is the initial value to get through this problem? Has anyone spotted that dollar amount? Awesome. Any volunteers for what it would be? Exactly. So the moment you see this right here, it's really a vocabulary question. They're talking about that quantity right there. Exactly. So all you have to do to solve this problem is just simply state it out. But I'm going to solve it in a weird way because this is a decent way to think of it too. An initial value is always V at 0. We have to calculate it if you would that way. And the punchline is it's definitely the 195,379. But if we inputted 0 into the function, it would look like this. 195,379, 0.73 to power 0. Because we're raising this quantity to power 0, that turns into a literal 1. And the whole thing that remains is the $195,379. So that's the initial value of this Corvette Stingray. Again, I'm not sure if that's a realistic value, but I think that's the better Corvette, so possibly. I agree with that. I mean, it's got a great engine and all that, but the interior is pretty bad on these cars. I think it's weird to spend almost 20% of $1 million and have the same thing in a Dodge car or something like that. But let's now take a look at next thing right here. We want to know predicted value after 7 years. That's no real different than what we did over here. We just calculate V at 7, which means we go to the original equation, put a value of 7 in for T, and that's the whole problem. So kind of the best word problems we've seen all semester, I'd say. Really the whole punchline to these is we're just getting used to working with an exponential function. So it'll go 195,379.73 to power 7. Now we got to throw all that into the calculator, and Desmos does pretty well for us. But I would say for chapter 6 that we're currently in, this would be a good time in the class to just routinely bring your calculator to class, because some of the things we have to calculate are definitely expected on a real exam, both on exam 3 and the final exam. We're gonna have to put in these things into our calculator and get our values out. So the more you practice in class, the more I'll be able to help if there's any problems working on your particular calculator. Oh, didn't mean to do that. For us, here's all we have to put in: 195,379. Then you could type this in verbatim in your calculator, the TI-32X2S or something like that, 0.73 to power 7. It's giving us this figure here. So after 7 years, that's a good time to pick up the Stingray. It's about 21,000, probably more its true value at that point. So 21,584, and we can round that to 30 cents since this is a money problem. 21,584 and 30 cents. So if you have your calculator with you today, or is that working out so far? Awesome, glad to hear that. If it's not working out, I'll be very happy to help out after class or anything like that. Also, even though we have Halloween today, I still have office hours 4 to 5 as well in the tutoring room. So that's, again, a really fast problem. It feels like for these, we'd be here all day trying to solve it, but really, it's all about just being familiar with the exponential functions, know how to get certain outputs out, like the initial value and some other value as well. Let's try this one here. Different situation. It says, suppose that the velocity v at t, so v for velocity this time, in meters per second, of a skydiver falling near the Earth's surface, that sounds grim when they say that, is given by the following exponential function, where time t is the time after diving measured in seconds. So at time 0, that's when you're about to jump. And at time 1, you just plug 1 right here, and that's how fast you're going according to this model. All it asks is, what is the velocity of the skydiver 45 seconds after jumping? But this one's actually kind of tricky to put in your calculator. Let me pull up a calculator to show what the actual problem is. That letter E, we're going to see this letter quite a bit, and E is Euler's number. And Euler is just a mathematician hundreds of years ago, but he was one of those strange mathematicians that all he did was math. He went blind at one point, and he still published volumes and volumes of math. If you took all of his published work, it could go from one end of the hall over there all the way to the other end, possibly multiple times. He was one of the most prolific mathematicians of all time, and that's his number, E. Turns out E is approximately 2.71 and is irrational. Let's put it into Desmos just to see what Desmos does with that. If you give Desmos E, here's what it gives us: 2.71828182, and it almost looks like this is a repeating decimal. And in some calculators, that's a real trick if they don't give you enough digits. But I assure you, this one's not repeating. It's just as irrational as square root of 2 or pi. And that's about its figure. E comes up all the time when you're dealing with exponential and logarithmic functions. But now to get it in your calculator, here's the struggle. We can't use the approximation 2.71. We need more accuracy. So we have to find it in our calculators. And in the TI-30X2S, see if we can blow that figure up. Didn't want to go to Amazon, but here we are. There we go. So what you need to do is, and oh, let me see if I can actually make this work. I'm trying to get a screenshot. Okay, that should be our screenshot right here. Let's just throw it in the notes to make it a little bit more available. I think it's the Amazon page on there. Well, I'll fix that up later on. So what we have to press in the calculator is, once I get all this back to working, almost there, hit the second key to start and the natural log key, and it will print out E like this, E to a power. All you'd want to do is put in the power of negative 0.26. We're going to do this at 45 seconds. So negative 0.26 times 45. And you'll have the right thing in your calculator at that moment. I'll try it in Desmos because that's the easiest calculator I have available. It's hard to show this as a screenshot with a real calculator there. But they're asking us, what's the velocity 45 seconds after jumping? On paper, I'd write V at 45 is 55 minus 55 times e to the power of, up here it's a negative 0.26. And here's where the input to 45 would go finally, right into that location. Which down below here, I'm just focusing on the base E exponential part. This is what it would look like in your calculator from here to the right. Now let's give this a try. Let me know if you're getting different values. I'll be very happy to help out with your version of your calculator. So going left to right, we would put in 55 minus 55, e to a power, negative 0.26, times 45. And this is what we would have as a result. This person, 45 seconds into their dive, is doing 54.9995 meters per second. It looks like they're pretty much doing their terminal velocity, which would have been 55 meters per second. If we put in 0, we get a value of 0, but that would make sense. 0 is when they're about to jump, right? They're not moving vertically downwards at all at time 0. 1 second later, they're moving 12 meters per second. 2 seconds later, it's 22 meters per second, and then it just keeps on going. But once we get to 45 seconds, we're extremely close to that terminal velocity of 55 meters per second for that skydive. So I'd probably take this. Let's put it in as 54.9995. And we can round this one. Let's round this to 55.0 meters per second. The 0.0 just as a reminder that it's not exactly that. We definitely did round this thing. But are folks getting about that figure there when throwing it into the calculator? Awesome, glad to hear that. And let's take another look on Desmos. Here's the other struggle about that number E. If we put in 2.171, it's, well, you know what? It's not too bad. That's not a terrible approximation. We get a pretty close value there. I was thinking it was going to be a little bit more off. All the way to a 5, then 272 versus E. Well, it differs at 1, 2, 3, 4, the 5th decimal place. I thought it would be a little bit more sensitive to that. I guess 2.71 is not a horrible approximation. But if you're missing questions in ALEKS, maybe your answers are a little bit off. It might be because we have to put in E exactly on those problems. Well, any questions at all, folks, on getting through the calculator on this one? Okay, definitely a weird topic, right? The struggle this time is not as much the algebra, it's more making sure we are telling the calculator exactly what we want to get through the problem. Now, here's our last one for today. This one is Definitely one of those Alex type problems that are extremely strange and a good one to bring to class. For if you see this one again, this is a good set of notes to return to. We have three different functions, and we want to determine which one is linear, which one is quadratic, and which one is an exponential function. Sometimes we can tell just by looking at it. A linear function has a constant rate of change. An exponential function does this. It has a constant ratio that we multiply by to get all to the next values. But looking at these, this can be a pretty tough topic. This is how I would probably start this off. Let's focus on just one at a time. So function one, we want to determine if it's linear, quadratic, exponential, or potentially none of these things. And here's what I would do to work on this topic. We want to look at all the differences on the y-coordinate here. From here to here, this difference is a +1. Let me make that slightly bigger. Going here to here, we have a difference of +6 altogether. Pretty much all I'm doing is taking the 14 minus 13 to get the difference. Here it was 20 minus 14 to get a difference of 6. Next one, I'll take 31 minus 20. This is a difference of +11 now. One last one, 31 minus 47 is a difference of let's see here, looks like a 16. So this one is definitely not linear. If it were linear, all of these would be exactly the same. A linear function has a constant rate of change. This rate of change is changing. So let's form the second set of differences. Here to here is +5. I'm really just taking the 6 minus 1 to take that next difference. 11 to 6, 11 minus 6 is 5. So we get to that 6 back to the 11 by adding 5 again. And same idea. From the 11 to the 16, you're just adding 5. So let's add some notes. These are the differences. These are the second set of differences. And we can now say here that if the second set of differences are constant, that's what we have. We have a constant set of differences, second differences, they're all 5. You are dealing with a quadratic function. Really bizarre topic. This would be something that we would cover as a really cool question if we talked about the differences at all in chapter 3, but somehow, some way, the math department just decided throw in this question in chapter 6 for no apparent reason. It's a cool question. It just comes out of the blue. We never talked about these topics. They weren't even in the book. But if you come back to these notes, this is the guide on getting through it. You just have to form differences in this way. And if you have the second set of differences constant, it's automatically a quadratic function. It's kind of an interesting way to see what quadratic functions are even doing in a certain sense. But let's try out another one, function number 2. So behind this door, we'll see what happens here. Any questions at all, folks, first about this one here? Okay, so for function 2, it's the same kind of game. We have to look at the differences on the y-coordinate here. So to go from here to here, I'm taking 5 minus 3, so that's really a 5 plus 3 altogether. The difference would be 8. Here to here, 13 minus 5, difference is 8 as well. Let me go plus 8 to just mention the sign. Take 13 plus 8, you definitely get to 21. Here to here, you can add 8 to get to 29 as well. And so now we can make a formula that says if the first differences are constant, that's what we have. We're constantly adding 8 to get to the next values as the x-coordinate changes by 1. Then the function is linear. So this is what a linear function would look like in this situation. Now, there's a couple strategies here. Truly, you could just take these 5 ordered pairs, plot them. It would obviously look like a line. That's a pretty good way to go through it. Plot all these, it should look like a polynomial, but that's pretty tedious. I think it's a lot faster to just do this operation, take away these facts, and then you can solve the problems much quicker. But if you don't care about first differences and second differences, that is an alternate strategy that you could use. So we had linear on this one. Let's try our last one and see what happens to that thing. Honestly, though, if you looked at it, I would say it's exponential because it's blowing up. It's getting massive as we go through here. That's almost a telltale sign it's got to be exponential. But the challenge is to prove it. It's got to do this. You need to find a constant thing to multiply by to get from one value to the next in that table. So back down here, way down here, I guess this is a good spot as any. Here's function 3. We went from -2 to -8, and we just have to say, what did we in fact do to go from here to here? We're multiplying by something, and you could say, that's just multiplication by 4, right? Then -8 times 4 is -32. And let me double check. -32 times 4. That gives us -128. At this stage, I'm pretty convinced it looks like we're just multiplying everything by 4 to get from one value to the next. And if you're multiplying to get to all of your next values, that's the telltale sign it's exponential. I'll put here just for a formula, since we multiply to get to successive values. So this is the telltale sign. You're dealing with something exponential in your process. Again, you could plot it, but that's extremely tedious. This is a much faster process. Well, any questions at all, folks, on getting through that topic there? Okay, it's a pretty weird one, but it's one of those kind of problems. We'll see how it goes. We probably won't see it again. I think it's a weird topic for sure. But it has its value. It's good to know if you have a set of points, what do they look like when they're really linear, really quadratic versus exponential? Well, I think it's a good stopping point for us today, folks. Any last questions before we call it a day? Okay, well, have a great Halloween, everyone. Stay safe, and I'll see you all in Thursday's class. Thank you.